Good morning. I'm here to talk to you a little bit about the OMEC project, which was announced, it's April, back in February. I was about to say last month, but it's a little bit too new in April. So OMEC is a project, right, that we want to really take VNFs intended for an open mobile core and move them toward production. So this project is based on a long-standing series of projects that we've been working with Intel since 2015, actually even a little bit earlier than that in terms of kind of the academic research space. And so it's really a next generation of several of our projects that have been out, like C3PO and NGIC, if you've seen some of our releases, I think going clear back to 2017. So this is a purely NFV architecture. It's a little bit older, right? We don't talk about cloud native. We are just focused on the network functions themselves. And you'll see that we really just kind of focus on different packaging options. So focused on production, right, we have to think about several things. So we have to think about connectivity, billing, and charging, right? So they're all slightly different activities within a mobile operator. We do have Release 13 kind of across the board. If you're familiar with, or not, with mobile networks, it's really hard to kind of pin down the radio side or the devices on a release number. So we just politely say we're somewhere around Release 13 if you're looking at eNode Bs or other items or phones. In general, the core itself of OMEC really focuses on Release 14. And if you actually look at all of our generate code and signatures, we're sitting between Release 14. And because we support option 3x, which is a Release 15 feature, you're starting to see now the code migrate into the Release 15-16 areas as new specs are defined. So this is not something sitting purely back on the older 4G side of this. We do support a large number of subs, and we're using DPDK underneath. You'll see us talk about different options in terms of control frames, but it's not unusual to see a single core in any uplink or downlink direction, basically pushing tens of gigs. And we're actually also providing all these services. So you still have the full features you would expect of an EPC running at those speeds with DPDK. So we're also optimizing, and we have been over the last couple years, and that's the new ngic code for smaller deployments, getting out toward that edge. And you're starting to see us also integrate some of the IoT application interfaces in the design. What's interesting about this project, I've worked on several open source projects as well, is we have a very rigorous CICD that we're pushing in. So we're not just worried about license checks, code commits, and stuff. We're actually pushing into the performance as part of the CICD. So we don't want to backslide. We don't want to find out later after we've done a code commit, we've accepted the code, we've got it running functionally. We don't want to find out later in the lab that the performance isn't quite what we thought it was. So we're really trying to push those traditional performance tests much earlier into the process. In fact, as early as we possibly can. And we're sitting out on GitHub. So when you wander into the GitHub repos, you'll see several things. Most notably, you'll see 3 very large projects, one called C3PO, which is the Clean Cups core with packet optimization. There you'll find the HSS, the PCRF for your policy. You'll find a lot of the SGX components for the billing side, as well as the charge trigger function, the actual guy that actually does the billing. You'll also see NGIC. We have essentially run a completion model in that, so you'll see it as NGIC, ngic-rte. You'll see that throughout the documentation. There, it's a split gateway, so you're going to see that control plane, that data plane connectivity, and that's where we use DPDK. That's where we're focused on the user plane and the performance. That data plane is the user plane here. Everything else you see is very much the control plane. A new project that has been brought in as part of OMEC is the Open MME. Now, if you look back to MCORD and kind of our legacy with MCORD, because a lot of these projects were in MCORD, the MME was actually another sub-project related to MCORD. In fact, there were several. If you looked right, there were several gateway projects. There were several MME versions. Here, what you're going to find in OMEC is you're going to find, at this time, essentially one location, one repo for each function. and we don't really intend to stray from that, although anyone's perfectly welcome to contribute even a redundant function within the architecture. But what we want to do is really provide a complete, consistent location where you can get all the parts you need through a finite number of repositories. We do acknowledge there aren't a lot of connections with the PCRF. You'll see later when I talk about in lightning talks, as well as here, we've got some plans to kind of close some holes here. So there are some other infrastructure projects that we have to worry about. Utils, we are an operator, and a lot of this code is being developed with Intel and with the operators. And so utilities, OSS, operational support system utilities, are their own repos and projects. It is a first-class citizen, although being a common function across all VNFs, right? We don't necessarily see it promoted up. Free diameter, which is a formal fork, if you're familiar with that, that's been around for years. We have quite a few improvements, including release 14, and I think after an angry letter last night, release 15 updates coming from a developer who didn't realize, he thought it was just release numbers are just a minor update. So unfortunately for him, that didn't quite work out so well. And then we've got the CICD resources, and that really ties into the ONF engineering team and what's going there with this. So this is all essentially that full pipeline. We do have, basically there's the what. I always get the what do you do. Default bearers, we're working on the dedicated, that's that PCRF piece I talked about. We have child protections. Part of being production, we have to remember, is legal compliance. So child protections is the thing first and foremost that we put into the even in the first iterations of the public code. And so that's always there. For the MME, if you're not familiar, it really is the kitchen sink of the mobile network. In fact, it has probably the most protocols I've ever seen of a functional elements. And tens of thousands of pages of documentation that are related to it in terms of what it implements. So we do have the basic functions of the MME, but keep in mind it would be a long way to go if we tried to do everything the MME does, even in the current designs. We do have, running into the code, what's referred to as user plane selection. So what's interesting about this is you're no longer tied to just statically saying, here's your control element, right? We have dynamic user plane selection based off capabilities and other items. That's currently in the select code, and we're actually pushing out updates to that. So you're going to see a little bit more dynamic behavior between the control and user plane, and really kind of updating to what I'll say, the best that could be provided in 4G for this type of work. And that includes, by the way, dedicated core networks. For a lot of folks, that's an IoT feature. It's a precursor to slicing, in fact, in terms of what they provided very early in the 3GPP designs. There's several things that are planned. A lot of people think of it as lawful intercept, but basically copying packets in the user plane and sending them. We tend to focus on analysis, troubleshooting with customers, those sort of things. Several roaming modes I'll go through, and kind of your usual suspects in terms of updates. There are a couple of communication modes with NGC. We do reference an external project under Open Daylight, a plugin called FPC Agent under what we'll call kind of the legacy mode. And then what we're doing is we're updating to the formal specification SX. So this is an unfortunate side effect of starting early. We actually released the code prior to SX's existence. And so sometimes when you're ahead of the spec, you do one design, and then as the specs actually get released, right, we migrate. So we are migrating toward this SX design. There are several deployment modes, and this is another common question we get about OMEC, which is, can we split the gateways? Can we converge the gateways? Currently today, we do a lot of testing on splitting the gateways. We do have a converged gateway kind of default mode over in the lower right, but it's not as thoroughly tested as we'd like. And we're also running through, at sprints, we're running through all of these permutations of testing. So we're, and we'll talk about it in lightning talks, but because not only us, but as a TST member, I know several operators are looking at least field trials this year. We're going through all of the different various modes that are possible with this code in terms of an operator testing. CICD, I mentioned before. What's interesting about this project, if you've used GitHub or other items, you never know what you kick off. I just want to remind people we're not just kicking off a little bit of your static check and other items. There's a lot of performance stuff going around the other side. The other thing we have as part of the project is another repo called IL Traffic Gen. It is a high-performance user plane data generation tool. And you can fit in traffic models, operator traffic models, those sort of things. So we also have that as part of the offering if you just want to download and look and see how far you can actually stress the performance. So once again, these are just frequently asked questions. I'll just kind of burn through these, right? So for diameter, we're release 14, and after we do some testing from some hateful developers, maybe release 15. GTP, we're very much, this gets back to kind of least common denominator with the eNode Bs. We're sitting at some of the lower numbers. My favorite question is what version you're at with an eNode B, and our response as the core team is whatever version it takes, because that's kind of realistically what goes on. And then we're primarily release 15 and release 14, 15 with some of the updates. So you're going to see us kind of basically support some of the 5G options that are coming in with OMEC, but we're not a standalone system right now. So deployment models, there's a deployment repo. We are legacy, right? So we're moving from kind of the old VM base. We have container options being pushed in as well. As far as cloud native, right, I will have to tell you our focus in OMEC is building the function and then tying to packaging. So right now we're maniacally focused on getting production capable functions. And so the real interesting question I'm looking at from a research perspective is if there's anything we need to materially change in the way we're doing the VNFs, right, which I don't know at this time, right, we'll make those adjustments as we understand. There are some Terraform scripts out there as well. So we are an open source project. We talk about contribution. Contribution comes in many forms. Bug submissions is probably the easiest way to get started. And documentation, complaining about our documentation, our READMEs, is also probably the easiest way to get in here. But I urge people, if you don't feel like contributing code, testing, or even just failing at a basic install can tell us a lot, right? Because we're unfortunately on the other side. We're the guys writing the code, so we know a little too much. If we look at functions, a lot of people ask where we can go. I would say the MME is always a lot of work to do for things, and the PCRF, we have a very basic one. We'll keep enhancing it, but if you're looking at and worried about trying to get into an area that's lightly focused on, those are two areas. So that's it for my time, so thank you.
All right, good morning, everyone. I'm excited to introduce a brand new project at ONF called COMAC. It stands for Converged Multi-Access and Edge. So you already heard about OMEC. OMEC is an upstream project that COMAC is going to consume. And this is a reference design and an exemplar platform project that ONF and the ecosystem will pursue. So what I'll do is I'll very briefly talk about the initiative, the supporting operators, and then the title says access and core. So I will try to explain what we mean by access and core in the context of COMAC. And then the CO in COMAC stands for convergence. But to be able to converge something, you have to first disaggregate. So we will talk about disaggregation and virtualization in a multi-access sense. And then that will lead us to convergence. But along the way, we'll also talk about how we can use SDN for programmable access, which is also an integral part of COMAC. And I'll very briefly mention the role of P4 towards convergence and the presentation by giving you a synopsis of how the COMAC edge will look like. So, like I said, COMAC is a brand new project. It is about a month old now, and right now the supporting operators for COMAC are AT&T, Deutsche Telekom, China Unicom, Google, Turk Telecom, and Sprint. So with this support, all of these operators are prepared to take this when the time comes to field trials. So let's talk about access and core. So we all know what really access and core mean from a wireless perspective. The access for a wireless cellular network is the radio access network, the RAN, which is composed of the base station and the handsets. And then at the core, we have in the LTE terminology EPC, or in 5G, ngic-core. And that provides, like Lyle said, which is actually OMEC, effectively. So that provides authentication, session management, mobility management, etc. So for the broadband side, the equivalent of that would be, if you are providing access to homes using a PON network, you would have a CPE at home, which takes you to an ONU, and then the fiber line would get terminated at OLT. So that forms the access equivalent for the broadband. And the core equivalent for as far as the broadband is concerned would be the BNG. So the BNG does a lot of the similar tasks that the EPC or ngic-core does. It does authentication, session management, etc., subscriber management. So let's continue on disaggregation towards convergence. So let's start with the radio cellular network. So the first step in the disaggregation is the disaggregation of the RAN. Following 3GPP on the path towards 5G, we can split the RAN three-way. We have a radio unit where the analog communication, most of the analog communication takes place. We have the distributed unit at cell sites where really delay-sensitive signal processing tasks take place. And then we have the centralized unit, which is virtualized and can sit at an edge cloud location and pool multiple DUs and RUs. On the core side, we have a CUPS solution. So the user plane and the control plane, like Lyle said, in OMEC, has to happen. The next phase of disaggregation would be, okay, I have a core control plane. I can further disaggregate that. I can, in the LTE lingo, I can talk about an MME, a gateway control plane, an HSS, a PCRF. If I want to go even further, using ORAN architecture, I can disaggregate the CU as well, so that I have a CUPS equivalent realization of the virtualized RAN. So this is how effectively you would virtualize the radio access network on the and the cellular network. On the broadband side, we have this setup with the PON and the BNG. So the disaggregation would take place at the BNG, and very much like the EPC, we would have a user plane and control plane separation. What that means for the BNG is at the control plane, there are a bunch of functions that I have to deal with now. The address management, the subscriber management, subscriber access management, the AAA functionalities, the service control, are all functions that the control plane needs to handle. So with that, I can also start talking about turning the access into a programmable entity. So those of you who are familiar with SIBA will all know that the white box realization of OLTs can have a hardware abstraction via Volta, which make them SDN programmable. So we would have an ONS application, a virtual OLT application that handles the programmability of the OLTs here. And on the cellular side, we could use ORAN specifications and develop a radio intelligence controller as an application sitting on ONS. And this, in return, would be able to control the DU, the CU, and even maybe the RU. So then this takes us to coexistence, right? The first thing that we ought to do to go towards convergence is to first test convergence, so coexistence. What does coexistence mean in that sense? Well, it is the capability for this disaggregated multi-access solution to share the same infrastructure. So if we are realizing this at the edge, this means the same leaf-spine fabric and the same cloud orchestration and the services controller to actually manage both of these access technologies. So here, as you can see, we have the same fabric shared by the cellular and the broadband network, and the overall containerized platform or VM-based platform is handled by the same orchestration, cloud orchestration platform. And I should note that this coexistence is being demoed at the ONF booth. So I urge you to actually go out and take a look at how this would work out in a core environment today. So now the next phase is convergence. Yes? Let me finish it and then do all that. So the converged user, so in terms of convergence, the first step is actually dealing with a user plane convergence. So in the disaggregation, I mentioned 3 distinct user planes, right? On the cellular side, the disaggregated RAN had a user plane CUU, sorry. And then on the EPC side or core side, we had the UPF. And for the broadband access, we had the user plane of the BNG. So towards convergence, the first thing that COMAC is going to do is converge those 3 distinct user planes into a single entity, which we call converged user plane function. So that will need to actually intelligently map itself to the associated control planes. So on the RAN side, it would need to communicate with the CUC. On the broadband side, it would need to communicate with BNGC. And on the core side, it would need to communicate with the control plane of the core network. Next step in convergence is actually the realization, potential alternative realization of the user plane using P4 as a solution that is executed right on the fabric. And that requires an SDN control, first pushing down the converged user plane as a P4 application to run on P4 capable switches, and then using P4 runtime to push down compliant, either BNG compliant or 3GPP compliant messages to control this converged user plane function. The next step in convergence is to start converging the control plane. So as I mentioned, in the BNG, both for the BNG and the core network, there are common features. Both deal with authentication, session management, subscriber management, policy management, admission control, address management. So these could definitely be converged. And actually, there is indeed ongoing work, both in the 3GPP arena and the broadband forum arena, and we will be following that work towards going towards a converged architecture here. And in the control plane, there will still be access distinct control functionalities like mobility management, which only apply to the cellular network and not necessarily to the broadband network. So this takes me to how this would all look at an edge. So we would base our edge on commodity hardware. So we would have a programmable SDN fabric. I don't know what happened here. Let me continue. We will have a programmable fabric on which potentially we will realize the converged user plane function. Thank you. We would then have if this is to be a cloud-native platform, we would have Kubernetes orchestrating all of the containers. And these, at the edge, these containers would be all of the control plane functions, as well as the cloud control and orchestration functions, and any third-party applications, either telco or OTT applications that require a presence at the edge. And then we would have a hierarchy of control planes, right? We would have a traditional ONS that would control the leaf-spine fabric, but that needs rules to be pushed down by the converged core control plane so that everything is 3GPP or BNG compliant. And then we would use ONS also to programmatically control the access components. This concludes my talk. Thank you. So if there's time, maybe I can answer the question now. Okay. Thanks.